Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is about calculating centre of mass of a lamina using integration. Let's begin with a problem. A uniform lamina is bounded by the curve y squared equals x. That's a parabola, but it's going to be a parabola with a horizontal axis. It's bounded by the line x equals 5, 2, and it's also bounded by the x-axis y equals 0, and we're talking about y is strictly non-negative. We're asked to find x bar, y bar, the coordinates of the centre of the mass of the lamina. Well, there's a picture. We can see we've got the upper branch of the parabola, we've got the x equals 5 as the right-hand limit, and we've got the y-axis bounding it below. And now we start an analysis. I'm going to take a thin strip of thickness delta x, which obviously will have height y in general, but in this case y will be equal to the square root of x. Now if we imagine that as being a uniform strip, it's very, very close to a rectangle, and the thinner we make delta x, the better that estimate of it will be. And if it's to be a rectangle, we know that its centre of mass will be right in the middle. So we can take its centre of mass as x y over 2. And its area will just be y delta x. So we can imagine the usual procedure of replacing a lamina, in this case a strip lamina, by a particle of the same mass with the centre of mass at its centre, since it's a rectangle. So there's our analysis, and we're going to use integration to form the sum for the various different strips that we have to add together. So let's go now to that picture and ask how we're going to go about doing that. Well, we're going to be interested in finding the area first and use the constant for the density, the surface density, in order to turn that into a mass. So we're going to be interested in the integral from 0 to 5 of ky dx, and that's going to be the mass of the lamina. So that's the mass. We're also going to be interested in the moments with respect to OX. Now that's going to be the sum of the moments for each element, and in the limit it becomes an integral. So as it is with an element, it will be ky delta x, which I won't write for a moment, but it's there, and then that's got to be, if it's about OX, times y over 2, because that was the distance to the centre of mass for the strip. Now I said I was going to add them all together and take the limit, so it will become 0 to 5, and the delta x will become dx. Similarly, there'll be an integral for the moment about the y-axis. Now in that case, the distance of the point, that point which represents all the mass, is a distance x. So we'll have again the ky, which represents the mass, times x, and again dx, because we're taking the limit for a lot of strips added together, all tending to in each case the width tending to 0, and we end up with that integral. So this is all about 3 integrals. Now at this stage I haven't introduced what the problem is. Well, apart from the 0 and the 5, I mean in general it would be a to b rather than 0 to 5, but I've done it with generality so that we can see where the terms are coming from. So what we've got then is that analysis. That's really a summary of what I've just said. The mass element is ky delta x, the centre of mass is for it is at x y over 2, and then the various moments give finally these integrals. So we now next want to go to introduce the specifics of this problem. So there's a summary of what we've got, and we need to introduce the fact that we know that y squared is equal to x, and it's the upper branch, so that tells us that y is equal to root x. So we need to bring in the problem. There we are, y squared equals x, which gives us, as I was about to write, that y is equal to root x for the upper branch. So that will equal, in this case, the 0 to 5 of kxy, so that will be k times x to the half, which is x to the 3 over 2 dx. Apart from the k, which is just a factor, that's standard integration theory. Similarly for the lower one, 0 to 5, and y squared is just x, so that's k times x over 2 dx, each of which we can work out. And for the total mass, it will be the area here, 0 to 5, not the integral here, k times x to the half dx. So the total mass this time is this integral, the total y moment is this one, and for the other one, the third integral. So it will be a matter of dividing this one by the mass and this one by the mass to get the two values of x bar and y bar. So that restates what I've just said. Y bar, you want the moments about the x-axis, which was the k times x over 2 integral dx, and the k root x dx for the total mass. So if we work that through, and similarly the x bar term will appear similarly. That's the other integral in the numerator. So if we work that through, it takes a bit of space to do it, so we'll do it separately, each of the two cases. So this was the first ratio for x bar. So we can see that the k, just as a passenger, it's a factor. So you're going to get the 2/5 from making 3 over 2 5 over 2, the usual integration formula, and the 2/3 from the x to the half in the denominator. We substitute the numbers. It's a bit complicated with the square roots, but 5 to the 5 over 2, 5 to the 3 over 2 will cancel to give just 5, and the k's cancel anyway. So finally, after all this, it's just 3. It's just a nice simple answer. There we are. Now for the other one, we've got x bar equals 3. The other pair of integrals, we were using the result that y bar times the total mass is equal to the total moment. So we make that into a ratio in the same way and work that through. The integration is a bit simpler this time. Of course, we've already done one of the integrals, the k root x one. So we work it through. X over 2 gives x squared over 4 when we integrate it. And this time it doesn't work out quite so nicely. It's 3/8 root 5. Now root 5 is a bit more than 2, so that's something like 3/4, which given the original picture probably seems about reasonable. It was the curve like that up to 5, and it was root 5, so this value is a bit more than 2. A bit more than 2. I'll put 2 plus, and we're saying that it's about 3/8 of that. So it's going to be somewhere about this level, which seems reasonable. And similarly, we got 3, which, given that there's more mass to the right than to the left, means that our centre of mass is going to come in about there. That seems reasonable. Okay, so the centre of mass finally is 3/8 root 5. Now, just to sum that up, going back to the most general, we had 0 to 5. I said it could be a to b in general. There we are. We ended up with these expressions x, y, y, and y squared over 2 and y as a consequence of thinking through how the moments of the strip worked and how we turned to the limit of integration. So these two formulae essentially are how to do it if it's a lamina, though I think it's worth always being aware how simple it is to derive them. Well, that brings us to the end of that presentation, and the final one is turning the integration results into their use for solids of revolution. So that will bring the whole thing to an end.